All right, let's see what we can do with this example. We've got a rectangular prism that is essentially a tank of some sort. It seems to be holding a bunch of, oh, what did I say, seawater? I believe so. I hope so, because I can't see the problem right now. We're trying to figure out how much it's going to take, how much work it's going to take to pump all the water out of this. It's coming out the top of the tank. There is a little pipe that comes out of the top, and that's where it's going to come out. Maybe there's a spigot, maybe there's just a hose, who knows? So the first thing you want to look at is, well, we're going to look at a very thin layer, just this, kind of layer on top. That's going to be our little increment that we're going to apply to figure out the work for this. And what shape is it going to be? Well, in this case, it's just a rectangle, isn't it? With a very little thickness. You've got the area of that times the thickness, which I believe is just, that's just a rectangle. 8 times 4 times dy. That's basically the volume. The area times the height, or the thickness, dy, is the volume. And if we want to find the actual force behind this, we just have to take that volume, well, times the density. It's what, 64 pounds per cubic foot. So that should give us a nice idea of what the force is. What is the distance that we're going to have to travel to pump this water out? Well, the whole tank is 5 feet high. The spigot or the hose goes 1 foot above that. So, whatever our height is, if we're imagining that this box is sitting on a nice level, it starts at a height of 0, goes up to a height of 5. We're going to have to pump it 6 minus y feet. So, if we're looking at this um, little bit of water here, and we're saying, oh, well, that's about 2 feet. The little purple rectangles that I drew in there is about 2 feet above the bottom. That means the water pumped out of that tiny little increment of water, or that tiny little increment of force there, is going to have to go up 4 feet. 3 feet to the top of the tank and 1 more foot out through the top, thereby allowing us to figure out exactly what the work for this will be. It's just going to be, well, 32 times 64 times dy. That was the actual force there. And then you've got the height. Well, you know what? This tank is 5 feet tall. That means there's a good chance that we're going to pump out from 0 to 5 feet. So at the very bottom of the tank, when it's almost empty, the last bit of water has to travel 6 feet up. At the very beginning, when it's completely full, the little bit of water on top only has to travel 1 foot. And that's basically the setup that you would have for this type of tank. Now in part B, I believe we're pumping water into the tank. I believe we're trying to do the exact same thing, but pumping water into the tank. So really, there's not that many changes here, are there? Except that, just because of where I did this, sorry, I know I put these numbers on the outside last time. You know what? The distance that it's traveling is just going to be y. Why do you ask that? Well, we're pumping water in right from the bottom. If the water comes in and has to flow up to a height of 1 foot, well, it's only travel distance of 1 feet. There's nothing extra to consider here. Now, I know that water is coming right into the tank at the bottom, but if the water flows into the bottom, it's pushing all the other water up to a height of whatever the current level is. So no matter what happens, as you're filling this up, if there's space 3 feet up, the water you're pumping in is going to either have to go up 3 feet to the top of that, or it's going to push other existing water up to 3 feet. The work is the same. So if you're pumping into a tank right from the ground level, the distance it travels is just going to be y. And that's it for the box example here. We'll look at a more difficult example in just a moment.